So first up, we have Dr. Pearson from the University of Alberta, and he's going to be giving our keynote presentation this afternoon. So please welcome to the stage, Dr. Pearson.
Thank you, Karen, and thank you for the invitation, and particularly for whoever was organizing the schedule for not scheduling me at 7:30 this morning. Thank you. So I'd like to, well, the aims of this, I was asked to say something about, give you the geological perspective about where diamonds are found and how we have historically found diamonds and where we might go next in terms of finding new gem diamond deposits. So we're going to look at the existing exploration paradigm in a geological context, and then we're going to explore some new aspects of the geology of the diamonds and their hosts that could take us in new directions to follow for diamond potential. And don't worry, you'll get your ration of gratuitous large diamond photos. There will be some diamond pictures as well. Okay, so I'd first just want to put the Earth in context. And so Daniel Twitchin this morning said that we can't see into the Earth, but of course, he's not a geologist, is he? So if you put the geologist spectacles on, then these are special spectacles that allow you to see into the Earth, which I'll now take off because I'll fall off the stage. Okay. But actually, rather like David Fisher's diamond spectacles this morning, the diamonds are our window. They're our lens into the Earth. And in fact, they give us the deepest lens of any natural material. So just to put the Earth into context, the Earth's radius is about 6,400 kilometers. That's about 4,000 miles for technologically challenged countries. And that 6,400 kilometer radius gives you a total volume of about 1.1 trillion kilometers that you've got to play with. And diamond is stable pretty much through all of that volume, in theory. Now, what we've been talking about mostly today are diamonds, let me rephrase that. Most of the diamonds, historically, we've thought to originate from this actually very shallow skin that we call the lithosphere. So the lithosphere is the skin of the Earth that's essentially cooled and is a rigid skin on something that is plastically deforming because it's very hot inside. And all these slides that you've seen with figures like 5 GPa and strange numbers like that, 5 GPa is roughly somewhere here, about 150 kilometers. And we think, or we have thought in the past, that many diamonds come from this sort of depth range between 150 kilometers and 200 kilometers. Now, the other thing I want to put in your minds is this concept of time, because this is very important in thinking about when diamonds formed, how the Earth works. So, rather like Salvador Dali, geologists have a very warped sense of time. And in fact, a really warped sense of time that usually involves beer bottles and stuff. But we're the sort of people that think that a million years is the bat of an eye, and most solid Earth geochemists and geophysicists are not really interested unless it's longer than 10 million years. And that's useful because when we think about diamond genesis, I mean, the Earth has this rich history of time locked up in it, 4.56 billion years of time. We're going to focus on this sort of latter 3/4 of Earth history. Here's 2 seconds to midnight on this clock where Johnny-come-lately human beings arrived, but everything else, all the interest for the geologists, happened well before then. We're going to keep in mind this key figure of 2.5 billion years, which, as we'll see, is important for the exploration paradigm, or has been important for the exploration paradigm, and I'm going to move this time as we go on. So let's just look at the basic bits of the paradigm. There's a little bit more to it, but in essence, this is the old exploration paradigm. And one of the parts of the paradigm was that diamonds are very old. And really that came from the fact that the first accurate age determinations, radiometric age determinations that were made on diamonds, on these rather nice heart spaghetti, beautiful purple garnets, came in at 3,300 million years. So about 2/3 of the age of the Earth. And that reinforced this idea that that diamonds are very old. And in fact, that idea really got put into the heads of diamond geologists and explorationists that most diamonds are very old. The other part of the paradigm is that diamonds are very deeply derived. And so most of us know that diamonds are erupted by this strange rock called Kimberlite. Here's an artist's impression of a Kimberlite. Nobody's actually observed a Kimberlite erupt, unlike any other volcanoes on Earth. And Kimberlites really are our planet's deepest derived volcanic rock. This shows what happens to them in the crust when they've got this grand finale of a very violent eruption here. I haven't shown the route because the route to those volcanoes goes down much deeper. So here's our 250 kilometer section again. Here's the Earth's lithosphere again, this thin skin. Here's the crust part of it, here's the mantle part of it. And these little things here are diamonds here. They're obviously not to scale, otherwise they'd be somewhat bigger than David Fisher's large sofa that we heard about this morning. But anyway, you can see them. And the Kimberlites are thought, really Kimberlites are a bit of a mystery. No one's exactly sure what triggers a Kimberlite eruption, but some deep level perturbance triggers what we can recognize as a Kimberlite volcanic rock somewhere round about the base of the Earth's lithosphere, and those volcanic rocks puncture the lithosphere, they pick up diamonds and they bring them to the surface. And if you happen to have thinner lithosphere, then you have a different sort of type of volcanic rock and you don't have the diamonds. Rather perceptively, this diagram was drawn in the late 90s by De Beers. Rather perceptively, you can see that they've even got little diamonds going way down here into the Earth's deeper asthenosphere. Okay, and then the other bit of the paradigm is that diamonds are associated with very old surface rocks, greater than 2.5 billion years. This is where this key age comes in. And so, of course, it's much easier to look on the land surface than to look beneath the Earth. And so here's a map of the Earth with most of the Earth's known diamond deposits on it. And the gray areas here are the rocks that we know are older than 2.5 billion years old. They're exposed at the Earth's surface. The brown regions are where we think there might be rocks of that age, but we're not really sure. And you can see that while there's good correspondence in countries like Canada here, you can see that actually there's not very good correspondence elsewhere, where there are the green diamonds, but really, actually, rather scarce amounts of actual 2.5 GA rocks, even though this is really in the exploration paradigm, or was at the time. And so the key part of that was that these ancient continental lithospheric roots here, so this is a cross-section cartoon drawn by my colleague Thomas Starkel. You see these deep roots. They've got ancient roots beneath ancient cratonic crust here, what we call those ancient parts of the Earth cratons. And another key figure to keep in mind is that actually that continental lithosphere is a mere 2.4% of Earth's volume, and the old bit of that lithosphere is less than 0.5% of that volume, so it's not very much of the Earth that we've all been looking for diamonds in. So let's see how we break this paradigm. One of the ways of breaking it is actually from the realization that the thick roots of continents do actually extend beneath crust of post-Archean age. In other words, crust younger than 2.5 billion years. And there's significant diamond potential in that lithosphere beneath that crust. So here is another type of geologist lens, not the special glasses, but the seismology lens, where we're using seismic waves to image the interior of the Earth. And so here are essentially slices, very like the tomographs that you see in medicine these days, where you see these three-dimensional images of the body. And these are slices through the Earth, or the body of the Earth, at various depths. So here's a slice at around 200 kilometers depth. And the important color here is blue, because blue equals cold, thick lithosphere. And actually these dark blue colors here indicate a wave speed anomaly of around about at least 2.5% here, and it's telling you that you've still got old, thick, lithospheric, well, certainly, no, it doesn't tell you anything about the age. Let's get this right. It tells you that you have thick lithospheric roots here to at least 200 kilometers. And if you compare that with the previous map, where you see you have these very gray areas here, and then you extend, you look again, particularly in, if If you compare, if I can work this, you can compare West Africa, Siberia, and Australia, where there are very few of these gray old areas, and then you look at the same areas, West Africa, Australia, and Siberia, you can see that there's thick lithosphere that could potentially host diamonds, and the huge areas there, much greater than you would guess just from looking at the areal extent of the very old rocks. Okay, so here's another way that the paradigm has changed over probably the last 15 years, and that is that diamonds, we now know, form through most of geological time, not just in the Archean. So here's time on the bottom axis here. This is carbon isotope ratio. For the purposes of this talk, it doesn't really matter. I just want you to focus on the time. And you'll notice that our magical 2.5 billion years here, yes, sure, there are diamonds that are older than that, and more of the measurements have confirmed that there are indeed these old Archean diamonds. But there's an awful lot more of the younger, the post-Archean diamonds extending way down into this area of the young Earth. So Dr. Wang this morning referred to these Zimi diamonds as old. Actually, those of us that work on old terrains in Earth would actually really think that these are quite young in geological terms. And then diamond formation right down to the time just before the Kimberlite erupts. And these young ages are now, there's more and more of them. They're very much accepted. When I first published this age here 20 years ago, we got a lot of flack for this. It wasn't very well believed in the industry. Okay. So instead of this paradigm where all diamonds are very old, then we have this picture where we've got diamond formation populating this huge area of time in the Earth. Looking a little bit deeper into this paradigm, we can look at the rock associations that diamonds form in. So there are two main hosts for diamonds, or at least in the old paradigm, people really focused all their efforts on two main lithological types, or rock types. One is Hartsbergite, that's characterized by these beautiful purple garnets, nice diamond there as well. This is essentially what you get if you melt the interior of the Earth's mantle, take a lot of basaltic melt out of it, for instance, to make oceanic crust. This is the sort of rock that's left behind. And then, if you take that oceanic crust and you subduct it back into the Earth, then you make a rock called an eclogite with nice diamonds. So these are, and you find diamonds in both these rocks. They were the two main diamond hosts. From detailed inclusion studies of the type done by Thomas Starkel and others, we built up this picture that in addition to Hartsbergite and eclogite, sure, they form the dominant host rocks for these diamonds with the inclusions in this case. Lithospheric, this rock called lithospheric, is a new contender here and a very important one in terms of being a diamond host. What's a lithospheric? Well, actually, if you take the oceanic crust and this, the residual mantle it melted from, and you put these two back together, you get this, which is a lithospheric. So if you use lithospheric and as part of the new paradigm, well, years ago, 20 years ago, all that the exploration industry were interested in, if they looked at garnet chemistry, this is a plot of chromium versus calcium contents for garnet chemistry, all that the exploration industry really were interested in were these garnets here, these lovely purple garnets, nice to look at, very distinctive chemical signature, low in calcium, high in chromium. Now we can see that there's a whole host of lithospheric diamond inclusions as well that clearly tell us that diamonds are forming in this rock that we call lithospheric. Why is this important? Well, in Canada there are two good examples of this. One in Saskatchewan, Fort Alacorn, and one in Ontario, the Victor Mine. And in both these cases, the inclusion suites are lithospheric. You have beautiful high-quality diamonds. These are probably the best quality diamonds in Canada from the Victor Mine. And Fort Alacorn, that's yet to come on stream, but may do shortly, also with spectacular diamonds, including some of the yellows that we've heard about today. And at Victor, this is inclusion chemistry from Victor, but at Victor and at Fort Alacorn, the inclusions are lithospheric. They're not the classic Hartsbergite, or there are some eclogites here, but on the garnet chrome calcium plot, the chemistry is very decidedly lithospheric. In fact, there are no Hartsbergitic diamonds there. And in fact, also, if you were to use garnet grains in your exploration model and go chasing across, well, it's not tundra there, it's more like bog, but anyway, if you're panning for heavy minerals and you look at the garnet chemistry, there's not a single, in the kimberlite itself there's not a single what you would call subcalcic high chrome garnet there. And if you're using that for your exploration paradigm, you will miss this deposit. Whereas if you're looking for lersitic diamonds, this gives you the clue as to what paragenesis the diamonds are. Okay. We seem to have stopped. Okay, maybe it was just a big image. Okay. So another part of breaking this paradigm is also the recognition that we said earlier that these lithospheres, these deep lithospheres, are old, and that was really the accepted knowledge until fairly recently, actually, very recently. So we'll focus on the Fort Alacorn deposit again here in Saskatchewan. So this is a very simplified geological map of Canada, and the reds, the pink, or whatever that color is, hue there, is the area occupied by, well, let's call it Archean to late Archean rocks, 2.5 billion year old rocks. And in Fort Alacorn, we know there are diamonds there, but there's been a great debate about how old the lithosphere is underneath, because there are very few good Archean rocks underneath there. So here are some ages that were produced by Yanina Chas in our department, dating, so these are not dating the diamonds, these are dating the lithospheric mantle keel beneath here. It's formation age, so you can't have diamonds residing in the lithospheric keel without the keel being formed. So this gives you a maximum age for the diamonds. There are as yet no dates for these diamonds, but I would levy a bet that they're going to be younger than 2 billion years. So this spectra here these are really the oldest ages there. We think the lithosphere there formed 2 billion years ago. In fact, there are hints in the crust that the oldest crust is 3.2 billion years. So there, in fact, in this location, there is not this coupling that we've come to expect between old deep lithosphere and old crust. The paradigm breaks down. 2 billion years is a very interesting time in Earth history, and there are other areas in Canada where that's an important time for lithosphere building. You know, just if you haven't acquainted yourself with the geology, so here's 2 billion years. It's in this eon that we call the Proterozoic, not the Archean. So there are two locations in northern Canada on Victoria Island and the Parry Peninsula here. They have kimberlites, and those kimberlites have diamonds in them. And sure enough, when we very recently dated the lithosphere there, here's the magical 2.5 billion year age line, and the lithosphere comes in there at both those localities at around 2 billion years. So there too, we've got this non-Archean lithosphere, but deep lithosphere. And as you'll hear later on from my colleague Thomas, there's really nothing special about the chemistry of the lithosphere in terms of its redox properties anyway, that lead you to think that you would make diamonds only under the cratons here. There are some other features that help that process. But in terms of pure redox chemistry, there's nothing special about that. And so there's really, that's helping fill in this picture of, well, we should start looking for diamonds and diamondiferous roots away from these classical, very old Archean areas that we think used to host diamonds. In fact, we can see very clearly that there's deep lithosphere under all these areas. So you might think that those two localities were, okay, there's no mines there, what's the big deal? But let's look at a rather more important locality, and that is in Siberia here. There are two mines, Mir and Udashnaya, that have produced the vast majority of the Siberian diamonds mined over the past 50 years. There they are. And if we then go and look in our seismic lens, we can see actually that there's a heck of a lot more lithosphere, deep lithosphere underneath the Siberian craton than you would imagine just looking at a map of the crust. And when we date the lithosphere there, this was work done by Dmitry Ionov a couple of years ago, you can see that, yes, there is actually a little bit of old Archean lithosphere further in the north, and even at shallow levels beneath Udashnaya, but actually these are ages of the lithosphere here. Here's the age, billions of years. 2 billion years is the blue here. The lithosphere age is 2 billion years, and the diamond formation ages start at 2 billion years and progress to younger ages there and even most of the crust there was built at 2 billion years. So 2 billion years, the Proterozoic is turning out to be also a very special date or time that we can think about in terms of places where we look for new diamond deposits. If you combine that concept with this Lurzolytic host rock that we're looking at, which actually forms a fair bit of that Siberian lithosphere, you can see from this plot, so this is a plot again of garnet chemistry. We like analyzing garnets and we like analyzing the calcium and the chrome. And you can see from that actually, so these are diamonds that were analyzed, the inclusions in them were analyzed by Larry Taylor and Nick Sobolev some time ago now, from exceptionally large diamonds from the Kremlin collection that somehow they got a pass to, as Evan put it, borrow them for the weekend and make the measurements. And you can see that these are 10 to 200 carat diamonds, and a good proportion of those diamonds have this Lurzolytic garnet chemistry as well. So you've got the 2 billion year age, and you've got Lurzolyte as perhaps a key diamond host in the Siberian lithosphere. And there's a lot of lithosphere to go at there. Okay, so lastly, we'll go and look at super deep diamonds. What I've focused on for most of the talk are what we now really refer to as shallow diamonds, the lithospheric component of diamonds that are derived from these keels here that extend, sure, a long way into the Earth, 200 kilometers into the Earth. But as we heard from the other talks this morning, and we'll hear from another talk later today, we have this category of super deep diamonds here, where for some time now, geologists have been identifying minerals included in those diamonds that give us clues that they come from very much greater depths than the lithosphere themselves. So here's a whole category of diamonds here that have nothing to do with the lithosphere. So you'd think that you can't really then use the lithospheric properties to prospect for those diamonds because they've got nothing to do with the lithosphere, at least in their genesis anyway. And so if we look at this large volume of the Earth that you've got to play with, instead of our rather piddling 2.4% of the Earth's volume of the lithosphere to play with, you've got 70-odd% of the Earth's volume to look at as a potential diamond host here. So a huge amount of new volume that can be explored as a potential growth site for diamonds. Here are the locations for super deep diamonds. The purple diamonds on this map, so to guide your eye, there are now something like 10 localities or so of super deep diamonds. There's a number in Australia, in Africa, 2 in Canada, and a famous one in Brazil here as well. And I'm sure there are going to be more to come. How do we know these are super deep diamonds? So this is the same sort of map that Evan showed, but this is for a paralytic lithology. So it's a map of pressure or depth versus where these minerals are stable. It's a mineral stability map of the Earth. And you can see from it that different minerals are stable at different pressures down within the Earth, and this is how we essentially extract the depth. We know this because we can make all these minerals in the lab. We can make these things down here by, funnily enough, squeezing 2 diamond anvils together and taking them to high pressure and stabilizing these high pressure phases. This is not a particularly attractive type 2 super deep diamond here from the Juina area, and some years ago we found the first terrestrial occurrence of ringwoodite, which is, I'm sure for most of you, a mineral you've never heard of, but it's about the 4th most abundant mineral in the Earth. It occurs down here in a depth range between 670 and about 520 kilometers, and it turns out that this mineral hosts most of the water in the Earth's mantle. Here's a synchrotron image of, actually there's 2 minerals. When you peer into this thing, there's 2 minerals. So we know that this is a super deep diamond because here's our ringwoodite, and right next to it is a calcium silicate perovskite phase in contact with each other, and that assemblage is only stable in a very tightly defined depth band from that depth range. So we've got super deep diamonds forming at depth in the Earth here. So this gives us this idea of a diamond factory at much greater depths in the Earth than just the Earth's lithosphere. Perhaps not everywhere, and what we think is that that diamond factory is focused around these subduction zones here. Here's the Earth's lithosphere, continental lithosphere, oceanic lithosphere. Here's a slab sinking deep into the interior of the mantle on this conveyor belt that's plate tectonics. And we have diamonds forming here in the asthenosphere, in this convecting part of the mantle, in this deep transition zone area, and then in the boundary between the upper mantle and the lower mantle here, where actually it turns out water is a very important part of this in the transition zone here. This is where really all the Earth's interior water is hosted. If you take a look at that, then literally the water shows up. I think the connection on this is... Okay. The reason I shaded that blue is to give you the idea that that's where all Earth's water is, and that's been indicated to us by that little ringwoodite inclusion in there. But also, ringwoodite is a deep blue color when we make it in the lab, and so if you were to slice the Earth open at that depth, you would find a color that was actually about that blue. We know from, really, this is where the GIA has come in. Their work, Evan Smith's work in particular, has shown that these super deep diamonds are really super special, many of them. Not the one I've just shown you, but many of these big diamonds now, and some of these beautiful pink stones and the blue stones are turning out to have super deep inclusions in them, derived from 700 kilometers depth or more. So here's an example from the Karowe mine in Botswana. This is an 800-carat, $60 million diamond derived from this hole in the ground. This is almost undoubtedly a super deep diamond. And at Karowe, anything less than 200 carats barely merits a mention. So this was just a random selection that John Armstrong, the guy that designed their diamond circuit, sent to me of their large diamonds. And I'd be willing to bet that the vast majority of these diamonds in this photograph are this super deep category. And we know that for some of them, because, well, actually not these big stones, but stones very much smaller, Thomas and I have a student, a Botswanan student, Thetsu Motsamai, and his thesis work has shown that the inclusions from some of those diamonds come in at around 420 kilometers, super deep depths. So really part of the future is going to be predicting with super deep diamonds, well, where kimberlites are that might have super deep diamonds. And that's no mean feat. I mean, hopefully we want to find super deep diamonds like this and not necessarily like this, although scientifically these things are just as interesting as these. But it's going to be difficult because there's this disjoint. We're not looking at the lithosphere here, and the lithosphere is physically coupled to the crust. These deeper parts of the Earth are in continued flow, and so we think that here's the diamond factory down deep in the Earth, and some precursor to the kimberlite may well be forming by some sort of thermal disturbance here right down at the lower mantle, upper mantle boundary, or by some drop in water solubility that creates a disturbance that melting basically transferring diamonds up here. And knowing the relationship between this and the continents at the time is going to be very critical. It's very hard to look at that now. Sure, you could say, well, why don't you go and use your seismic lens to look at this? So here's a seismic velocity profile, a slice through the Earth at 670 kilometers. And the key thing to know about this is we see this today. Those diamonds that erupted on the Earth's surface erupted 90 million years ago. So there's a time disjoint that we've got to try and fill in somewhere. If you just take a look at this, there's very little correspondence between any pattern on this S-wave velocity map and any location for super deep diamonds. So that's where the challenge is going to be. But it's going to be a challenge with very rich rewards. So in summary, while we've greatly increased the volume of Earth the diamonds appear to be derived from, we've vastly increased the area over which diamonds may have been brought to Earth's surface, and we've diversified the source rocks that host diamonds. All the low-hanging fruit's gone. And that's the case for pretty much every mineral deposit on the Earth. All the obvious stuff has been tripped over and found, and we're going to have to be a lot smarter about finding the new things. And so to finish, I'll leave it there. Thank you.
Thank you very much, Graham. Does anyone have any questions? Go ahead. If you can just walk up to the mic here, please. Thank you.
Thank you for helping us break the paradigms. Your map of global diamond occurrences had one called UHP crustal
Yes.
on the coast of East Australia. Can you speak to how that would break the paradigm?
Yeah, there is some debate about how that is classified. I think so what that is plotting are a group of diamonds from Eastern Australia that occur in the Copton area, and they have extremely strange calcium silicate inclusions. And that's not my label of those diamonds, but they're so strange in terms of their inclusions and their carbon isotopic signatures that people have sought to explain them most conveniently by them simply being pieces of continental crust. So calcium-rich phases are very common in the continental crust, calcium silicates and calcium carbonates, and if you take them into the diamond stability field, you make diamonds, and then you exhume those rocks, you'll get diamonds with that very strange inclusion assemblage. And so that's part of a number of occurrences around the world where there are these crustal ultra-high pressure rocks. They're clearly of crustal origin. We know what the isotopic signature of continental crust. We know what crustal rocks look like. That's, our geology lenses are a bit blurred, but they're most sharp in the continental crust because we can see it in front of us and we can recognize when rocks like that have been put into the diamond stability field and brought back up.
Would that not open up a much younger window of time and also a much shallower domain?
Yes, yeah. I mean, you still have to get them into the diamond stability field. I think any area of time is open for making diamonds. Any area, any part of the geological timescale.
Any further questions? If not, let's thank Dr. Pearson again. Thank you so much, Graham.